Hello everyone. In this video, I will be going through some of the questions on your Test 2 review project starting from question 5, and I will explain the solutions to these questions. All right, so we will start with question number 5. It says here, given the accompanying ANOVA output for a randomized block design experiment, answer the questions that follow. So we have been given an ANOVA table here. We have not been given the details of the experiment except that it is a randomized block design experiment. So based on the information contained in this ANOVA table, we are going to have to answer the questions that follow. So let's look at the table. We have here three sources: the block, the treatment, and error, and this last row is for the totals. All right, and then we have the DF, degrees of freedom, for each of the sources. We have the squared sums, sum of squares, and these are the values pertaining to each of these sources: block, treatment, and error. Then we have the square of the means, followed by the F statistic, and then the p-value. The last column is the p-value pertaining to the F statistic over here. All right, so given this information, let's answer the questions below. A says, find the value of A in the total row, which is the DF total, the degrees of freedom. This column here represents degrees of freedom. They want the value of the total of all these degrees of freedom. All right, so this should be pretty straightforward. All we are doing is adding the degrees of freedom for each of these sources. All right, starting with block DF, treatment DF, and error DF. All right, so I'm going to write it down here. The answer is going to be 12 plus 2, 14, plus 6, 20. Correct? So the formula is going to be block DF, treatment DF, plus error DF, and let's write the values below. It's 6 plus 2 plus 12 is 20. All right, so the answer, the DF total, is going to be 20. The next question says, find the value of B, or SST, square of sums total. All right, so SST again is the sum total of block SS, treatment SS, and error SS. So let's write that again. Block SS, just make sure you're summing up the values in the right column. Then we have the treatment SS, followed by error, or SSE as it is called. So block SS is 1637.81, and then treatment SS is 707.43, and SSE, or the error sum of squares, is 413.90, and that gives us a value of 2759.14. So let's write that answer in this cell, 2759.14. The next question, C, asks how many blocks were used in the experiment. So they want to know the total number of blocks. Now, since they haven't provided us with details on the question, it doesn't tell us how many blocks were used directly. We can know that by looking at the DF value. All right, so the number of blocks is going to be one more than DF, because the formula to calculate the DF for block is number of blocks minus 1. That gives us the DF value. So if DF is 6, then the number of blocks is 1 more than the DF, which would be 7. All right, so it's going to be number of blocks used is 7. And how did we get that? It's the DF for block plus 1. Correct? We use the formula for DF to back calculate the number of blocks. D says how many treatments were used in the experiment. It's the same way. The DF for treatment uses the formula number of treatments minus 1. All right, so that means the number of treatments must have been 3 in order to get a value of 2 for the DF, correct? So I'm going to say 3. How did we get that value? That's treatment DF plus 1. All right, so treatment DF was 2, therefore plus 1 is going to give us 3. Right, now part E says the DF for error is given as 12. How was that calculated? Now, in questions for block design, in experiments that use randomized block design, the way we find the DF for error is going to be the DF for the block multiplied by the DF of the treatment. So I'm going to write that as block DF multiplied by, again, multiplication, not addition, multiplied by treatment DF is going to be the error DF. So block is 6 multiplied by treatment DF is 2, therefore error DF is 12. All right, that's how they came up with this number here. Let's go on to the next one. Now, let's look at question number F. It says, the researcher wants to conclude if the null hypothesis mean, which states that all the means are equal to each other, against an alternate hypothesis, which states at least one of the means is different at a significance level of 0.01. Based on the ANOVA table given up there, what should the researcher conclude? So this is a multiple choice question, but let's look at the p-values in the table. Now, when we are comparing treatments in randomized block design method, we are not concerned with the difference of means between the blocks. We are only concerned with the difference between the treatments, the mean values between the treatments. So we are not going to focus on the block row. We will just focus on the treatment row and pick up the p-value here, because we are going to use that to answer the question in F. So let's go through the choices. They've given us the p-value we just obtained was 0.0003. Correct? That was the p-value on the table, and the alpha value is 0.01. So the choice A says the researcher should reject the null hypothesis that the population means are equal because the p-value is less than alpha equals 0.01. So yes, the p-value is indeed less than 0.01, correct? 0.0003 is less than the alpha value 0.01. So if p is less than alpha, we reject the null hypothesis, correct? So this looks like it would be the correct choice. I'm going to circle it for the time being, but let's go through the rest of the choices. It says the researcher should not reject the null hypothesis that the population means are equal because the p-value is greater than alpha equals 0.01. This is not true. P-value is 0.0003 is less than 0.01, and that's the reason why B is not the right choice. C says the researcher should reject the null hypothesis. So reject is fine, but that the population means are equal because the p-value is greater, right? So this doesn't match. This is reject, but p-value cannot be greater than alpha in order to reject a null hypothesis. So this is out. And then For D, it says the researcher should not reject the null hypothesis that the population means are equal because the p-value is less than alpha equals 0.01. No, if p is less than alpha, one should always reject the null hypothesis. So the only one that agrees with the p-value and the alpha value and the comparison between the two is A. Right? The researcher should reject the null hypothesis that the population means are equal because the p-value is less than alpha equals 0.0. Okay, so part G says what is the mean square due to error? In other words, what is MSE? Let's go up to the table. MSE is what we are looking for. So you have to look in the column labeled MS and then the row which is error, MSE. So MSE is going to be 34.492, correct? So let's write that down. We are just picking that value from the table, 34.492. Part H pertains to part G. It says show the calculation below by which MSE value was obtained. The formula to calculate MSE is SSE divided by the DF for error. Alright, so it's SSE divided by the error DF, correct? So how much was SSE? Going up again, it was 413.90. 413.90 divided by error DF was 12. When you perform that division, you should come up with a value of 34.492, what we wrote up here. These should match. All right. What is the mean square treatment? Again, you can go up the table and you will see it's 353.714. It's the treatment square. All right. So let's write that value here, 353.714. And how did we perform that calculation? MSTR has the formula SSTR divided by treatment DF. All right. So SSTR was 707.43 divided by 2, which is the treatment DF. So it gave us a value of 353.714. And then the final question pertaining to this particular problem, it says explain if Tukey's test should be performed on this data. Choose the correct answer below. So it's not always that you should perform a Tukey's test after completing a hypothesis test. The only time a Tukey's test will be performed is when we reject the null hypothesis. Because if we do not reject the null hypothesis, that means there is no difference between the means. The means are close enough. They are almost the same. All right. There's no significant difference between the means if we do not reject the null hypothesis. So a Tukey's test comes into play only when we reject the null hypothesis, stating or asserting that there are some means that may be different from each other, and the Tukey's test help us determine which means are different, which means are not different, and so on. All right. So given these choices here, number 1 says yes, Tukey's test is only used if the null hypothesis is rejected. So we rejected the null hypothesis, so you may have to go back and check if you have answered this question correctly, F, then you should be able to answer K correctly as well. It should be the first one. The second one says no, Tukey's test is only used if the number of treatments is not large enough. No, that doesn't apply. That's not correct. 3 says no, Tukey's test is only used if the null hypothesis is not rejected. Absolutely not. And then 4 says Tukey's test is only used if the data are not from a population that is normally distributed, right? So the only one which makes sense, is yes, we still have to perform the two keys test because we have rejected the null hypothesis. There is a difference between at least some of the means, so we need to go further and see which means differ, how significantly, and so on. All right.